Hi, this is Mr. Conti, and in this video we're going to go over the review for Unit 2 on constant velocity. There are 5 questions, so let's take a look at number 1. So in number 1 we're given a position time graph, and in part A we're asked to determine the average velocity, and in part B we're asked to find the mathematical equation that describes the motion of this object. Well, let's go a little bit further. What else can we say about the motion of this object? Well, the object starts at the location x equals 10 meters away from the origin. So I'm going to just write that down. x0 equals 10 meters. Okay, it's moving in a positive direction and has a constant speed because it's linear. And what speed it's moving with is going to be determined based on finding the slope of this line. The slope tells us the speed and the direction. So to find the speed or the velocity, we're going to use delta x divided by delta t. So this is just the slope formula when you're looking at a position versus time graph. So I want to pick 2 points. So I'm going to pick the endpoints here that look pretty clear. The point here is time 0, the location is 10 meters. And here at time 6 seconds, the location is 60 meters. So we do the change in position, which is 60 meters minus 10 meters, divided by the change in time, which is 6 seconds minus 0 seconds. So on top we get 50 meters divided by 6 seconds, and our final answer is 8.3 meters per second. So that's the velocity, the average velocity for this time period. So v equals 8.3 meters per second. Now the general equation for this line looks like this: x equals v times t plus x initial. And so to write down the specific equation that maps this motion, we just plug in the slope that we got, which is the velocity, and the intercept, which is the initial starting point. So we get x equals 8.3 meters per second times t plus 10 meters. In number 2, we're given a velocity time graph and first asked to describe the motion. Remember, on a velocity time graph, you don't know where the object is moving from, but you can determine how far the object travels, in which direction, how fast, and at what time. So we're going to first describe the motion of the object. So let's see. The first thing we can say is that it's moving to the right with a velocity of positive 4 meters per second. That lasts for 2 seconds. Then it moves to the left at a velocity of negative 3 meters per second. And then that only lasts for 1 second, and then it stands still with no velocity at for 2 seconds. In part B, we're asked to draw the position time graph. So we'll try to make this as quantitative as we can. Again, we don't know where the object starts, so we could choose any intercept that we like, but because the object is going to be moving forward at a fast rate, we should probably start our object at the origin, considering it's going to go in a positive direction. So it's going to move 4 meters in 1 second, and it's going to move a total for 2 seconds, so it'll cover 8 meters. So we'll draw a line with a positive slope, and this will correspond to the time 2 seconds and the location 8 meters. It's then going to move backwards at a rate of 3 meters per second. So it'll backtrack 3 meters, so it won't be quite as steep. And so this now represents 3 seconds, and the location here is 5 meters, having backtracked 3 meters. And then for the remaining time, it will remain at rest, so that's a horizontal line for the remaining time. How far did the object travel between 1 and 2 seconds? Well, from the position time graph that we would draw, we'd have to know where the location is at 1 second. So with a slope of 4, it goes up 4 over 1. So at 1 second, it's at the location 4 meters. At 2 seconds, it's at 8 meters. So the way we'd get this from this graph would be to say that delta x equals x final minus x initial. So 8 meters minus 4 meters equals 4 meters. If you wanted to get that information from the velocity time graph, here's our graph between 1 and 2 seconds. Remember that the boundaries are between the graph and the t-axis, and then we enclose just that interval. And the region that we shade in there, that is going to be the displacement if we find the area of that shaded region. So the displacement, or the area, equals, we have a 4 by 1, so 4 meters per second in height, and the width is just 1 second. And so there you get 4 meters as well. So these two results match. Now it says, what's the total displacement for the entire graph? Well, again, we could use both graphs to show the work here. By looking at our position time graph, we see that the object starts at the origin, and having carefully drawn this out quantitatively, we know that after 5 seconds it reaches the location 5 meters. So it went further, but then it backtracked. So we only care about those 2 points here, the difference between where your object started to where your object ended up. So here delta x is 5 meters. How you would get the same results is by looking at the velocity time graph and working out the area of the entire graph. So the region that we're going to shade in includes the t-axis. Now with the graph being up here, we'll box this area in. But then from 2 to 3 seconds, the graph is down here. So it's going to be this region that we box in. And then where the graph is on the t-axis, it has no area. And that makes sense because the object isn't covering any distance. So we are going to work out what the area of this block is and the area of this block, add them together, and that'll be your total displacement. So this is a 4 by 2, so we get 8 meters. That relates to the fact that from the start, the object travels 8 meters this way. This has dimensions of -3 by 1, so this is -3 meters. And that shows that the object backtracked 3 meters this way. So 8 meters plus -3 meters equals 5 meters. If you were to add both of these quantities without the negative, you'd get 11. 11 meters would represent the distance that the object traveled, where we would continue to rack up the length of the path that the object had followed. Alright, number 3. Johnny drives to Wisconsin, which is a 1,920 mile trip, in 32 hours. He returns by the same route, so he travels the same distance, in the same amount of time. What's his average velocity and his speed? So the speed, the definition of average speed is the total distance over the total time. So the distance does not depend on the direction. So the fact that Johnny turns around and goes back, he's still adding to the total distance that he traveled. So the total distance is 1920 miles plus 1920 miles. So you get a total of 3840 miles. 3,840 miles. That's the total round trip. Now, it takes him 32 hours to go and 32 hours to come back. So that's a total of 64 hours. So we did the total distance and the total time. If we divide them through, you get that the average speed is 60 miles per hour. What's the difference between speed and velocity? Velocity takes into account the direction. So it's going to matter that Johnny moves in one direction to go and moves in the opposite direction to come back. You can say that part of the motion is positive and part of the motion is negative. So ultimately what we're going to want to determine is the total displacement that Johnny underwent in the total time. So because Johnny ends up going and coming back along the same path, he returns back to the same position that he started from, the total displacement is 0. So even in that 64 hour time interval, you still get that the average velocity is 0 miles per hour. And all that means is that if the object is in motion and has an average velocity of 0 miles per hour, that the object has returned back to where it started. So some of the motion was positive, some of the motion was negative. The average works out to be to 0. So these two values are different because speed does not take into account direction, whereas velocity does take into account the direction. So make sure you use these formulas when calculating average speed and velocity. Number 4, we want to describe the behavior of this object, which is on a qualitative velocity time graph. There's no numbers here, so we're just going to qualitatively describe what's going on. So this object is moving to the right with some positive velocity, and sometime later, if we took these to be seconds, this would be 1, 2, 3 seconds in, moves with a slower speed to the left. We're asked to draw a motion map. Again, we don't know where the object is, but because the object is going to start by going to the right, let's draw our first dot as far to the left as possible. So this is going to be our origin. Now, if we assume that each of these are seconds, 1, 2, 3 seconds, then this is time 0, and we're going to draw large arrows that point to the right. That's 1 second. That's 2 seconds. And at 3 seconds, the object is ready to turn around. So all these arrows should be the same length. Now, in the turnaround, because if I place my dot here, to go backwards, I'd be overlapping the arrows. I'm going to lift this dot up and place it here. And now the arrows that I'm going to put afterwards, which count for 4, 5, 6, and 7 seconds, are going to be pointing backwards and shorter. So this dot is 4 seconds in, 5 seconds in, 6 seconds in, and at 7 seconds we don't know what it's doing. So that's the total graph. Now we could also draw, it didn't ask us to do it, but let's draw a position versus time graph. Now we have to make sure that our graphs agree. So on our position time graph, because we started our motion map at the origin, we're going to start our position time graph at the origin, and we're going to show a fast positive motion, so steep and moving upward, and then a slow negative motion. So the graph is coming back down and not quite as steep. Alright, last question. This is a word problem. A race car travels at a speed of 95 meters per second. How far does it travel in 12.5 seconds? Use appropriate mathematical expressions and show how units cancel. Keep the proper number of sig figs. Alright, so this has 2 sig figs. This has 3 sig figs. Anytime you're going to do any sort of multiplying or dividing with these numbers, you're going to go with the least number of sig figs. So your final answer is going to only have 2 sig figs in it. But let's talk about the problem solving strategy that we went over in class. We have 3 variables that we want to talk about. Delta x is our displacement. A lot of times it is also related to distance. Velocity, which in many problems is related to speed, and time. What you want to do is construct a simple known and unknown table to list what you're given and what you're asked to find. So the speed, 95 meters per second, is our velocity. So I'm going to write in the known column 95 meters per second. 12.5 seconds stands for the time. So that's delta t equals 12.5 seconds. We're asked to find how far. How far is a measure of the displacement. So now I want an equation that relates these 3 variables. If you think back to the slope of the position time graph, you get that velocity equals delta x over delta t. So this may be one way of remembering that formula. But what we want to do first then is to solve for delta x. And what we'll have to do is we'll have to multiply delta t onto both sides. So if we multiply delta t to both sides, we lose the delta t here, and we gain the delta t up top next to v. So to solve this problem now, we're just plugging in, substituting in the values, 95 meters per second in for the velocity, and 12.5 seconds for the time. So according to the calculator, we get 1,187.5, and the units work out where the seconds cancel and you're left with meters. So that is, according to the calculator, the correct answer. But when you're talking about measurements, your final result can only be as accurate as the least accurate measurement in your calculation. So the fact that this is only to 2 sig figs means that this answer can only be as accurate to 2 sig figs. So right now there are 5 sig figs here. To reduce it down to 2, we're going to round this 3 times. So we're going to bump the 7, we're going to get rid of the 5 and bump the 7 up to an 8. We're going to get rid of the 8 and bump this 8 up to a 9. And we're going to get rid of the 9 and bump this up to a 2. And we get 1,200 meters. To make sure that these zeros don't count as significant, I could put a line over top of that 2, or I can write this as 1.2 times 10 to the 3rd meters. Or better yet, I could write this as 1.2 kilometers. And again, now my answer is to 2 sig figs and with correct appropriate variables. All right, thanks for watching.